Thank you everyone for attending. I'm Jaehoon Lee. Also, thanks to the organizer for this interesting event. In this lecture, I'm going to talk about minimal surfaces in R4, like the Lagrangian Cartinoid. This is part 1 of the lecture. The main results will be presented in part 2. So in part 1, my goal is to give some motivation for this work by describing the properties of the Lagrangian Cartinoid. And also I will cover what is needed in the proof of the main result. Okay, then let me start with the Lagrangian Cartinoid. The Lagrangian Cartinoid in R4 can be identified with the following set. It is given by the graph of a holomorphic function 1 over z. So it is a holomorphic curve in C2. Here and later, we will always identify C2 and R4 by this correspondence. As it is a holomorphic curve, it can also be considered as a minimal Lagrangian for some orthogonal complex structures in R4. So it was one of the special Lagrangians constructed by Harvey and Lawson. It appeared in the paper on calibrated geometry, and their original purpose was to provide special Lagrangian examples that are invariant under the diagonal action of the special orthogonal group. Now, let's take a closer look at how the Lagrangian Cartinoid looks like. First, it is circumfoliated. To see this, express Z in a polar representation. Then the point on the Lagrangian Cartinoid can be written as a point in R4 as follows. And we may separate this expression into a linear combination like this. So the image of this set is a circle of radius r square plus 1 over r square, where the circle lies on a plane generated by these two vectors. And Next, it is asymptotic to two planes. As r goes to 0, these planes or circles converge to the w-axis. Here it is the w-axis. And similarly, as r goes to infinity, the plane converges to the z-axis. And in both cases, the radius getting bigger and bigger, so it looks like that start from a small circle here, and it's getting bigger and closer to each coordinate axis. Here it is t equals 0 and w equals 0. So it is a doubly connected complete example. And finally, one can see from the Gauss-Bonnet theorem that it has a total curvature minus 4 pi. Lagrangian catenoids have been shown to be interesting examples in several studies because they satisfy many good properties as in the above. The following are the results of Castro and Urbano. They proved the results in arbitrary dimension but only introduced two-dimensional case. Okay, so in the same paper, they characterized the Lagrangian catenoid as a non-flat circumfoliated minimal Lagrangian in C2. And they also characterized as a non-flat complete minimal surface with finite total curvature, where the compactification by the inversion is Lagrangian. Here, the inversion is given by this. These characterizations are related to the Lagrangian condition. Now, we will see how the Lagrangian catenoid has appeared in the minimal surface theory. First, Hoffman and Osserman classified complete doubly connected minimal surfaces in Rn with total curvature minus 4 pi. And the Lagrangian catenoid is one of them. And Park proved that circumfoliated minimal surface in Rn not contained in any three-dimensional affine subspaces is the Lagrangian catenoid. So he was able to prove that there is no counterpart of Riemann's minimal example in R4. Also, Lee obtained the above Hoffman-Osserman surfaces, these Hoffman-Osserman surfaces, by applying complex parabolic rotations to the holomorphic curves of the catenoid. Lee here is not me, it is our organizer Hosu Lee. Besides the above results, we are interested in its asymptotic behavior. So let me introduce our main questions. Question 1 is, can a minimal surface in R4 with ends like the Lagrangian Cartinoid have a positive genus? And question 2 is, can a minimal surface in R4 with two embedded planar ends have a positive genus? Note that the first question is more restrictive, and we will explain later what it means for ends like the Lagrangian Cartinoid, and embedded planar ends after we recall the generalized Weierstrass representation formula. So, why these questions are interesting? First of all, the Lagrangian Cartinoid makes difference between R3 and R4, as there is no complete minimal surface in R3 with two embedded planar ends. Also, there are many results on minimal surfaces with embedded planar ends in R3 because they are also related to Wilmore surfaces in a sphere. So it is curious about that how the results will change in high codimension. Moreover, questions about the raw number of ends are interesting because for low genus and many ends, there are many examples in R3. So in R4, and for large genus and many ends, we have some hope for applying gluing methods or some technique of adding handles. So the low number of ends case remains. Okay, now we will see some results in R3 before we begin the discussion in R4. Here we collect some result in R3, and the end always means an embedded planar end. Embedded planar end. So only a plane can have one end by the maximum principle, and there is no example of having two ends. And for a punctured sphere, we have the non-existence of 2, 3, 5, and 7 ends. Otherwise, examples have been constructed in all cases. And for a punctured torus, we have the non-existence of 2 and 3 ends. In this lecture, we are mainly interested in the non-existence of a low number of ends, so it would be nice to remember this non-existence result for 2 and 3 ends. Okay, now let M be a complete minimal surface in R4 with two embedded planar ends and finite total curvature. Then M is given by an immersion X from a punctured Riemann surface sigma into R4, which is given by the real part of this integration with 4 conditions satisfied. Note that here phi 1, phi 2, phi 3, and phi 4 in projective space P3 can be considered as the generalized Gauss map. Here we say the end is an embedded planar ends if it is asymptotic to a plane and it becomes a graph over that plane outside some compact subsets. And if it has no logarithmic growth, has no logarithmic growth. So if all these 3 conditions are satisfied, we say that the end is embedded planar ends. So the round number 4, the number 4 here, exactly describes the conditions of the ends. Okay, then let me describe what it means for ends like the Lagrangian Cartinoid. From the definition of the Lagrangian Cartinoid, we may compute the generalized Gauss map as follows. Here the image lies on a quadric in P3, and from this the Gauss image at limit ends are given by the following. Now it is well known that the quadric is a ruled surface. These are rulings, two family of rulings. And it is easy to see that these 2 points are on the same ruling, like this and this. So we call a surface has ends like the Lagrangian Cartinoid if it has embedded planar ends and additionally all the Gauss images of limit ends are on the same ruling. Okay, finally we discuss meromorphic differentials in the generalized Weierstrass representation to make them in a more organized form. We recall the following two facts. The first one is Riemann log formula. Here L is a line bundle and here K denotes the canonical bundle of sigma. And here G is a genus. And next is a residue formula. So if L was the canonical line bundle K, then the above formula implies that the dimension of this space is equal to G. Here, this space is a space of holomorphic worm forms. So it means that the space of holomorphic worm forms has dimension G. Next, for distinct points P1 and P2, define the following three line bundles. Then, again by the Riemann log formula, we may compute a dimension of each space of holomorphic sections. Roughly speaking, the expression in the bracket gives information about possible pores. For example, this is a space of meromorphic worm forms with n-most double poles at P2. By dimension counting and applying the residue formula, we may choose the following elements: eta 1, eta 2, and eta 3. We will make a special choice of these differentials in part 2. And by the residue formula and each eta 1 and eta 2 have double poles at P1 and P2 respectively, so note that eta 1 and eta 2 have no residue. So in summary, we constructed a basis G holomorphic one forms and eta i's form a basis for this space, and so we may write phi j as a linear combination like this. Here omega j is a holomorphic one form and its coefficients are in complex field C. Because phi j and omega j and eta 1 and eta 2 have no residue, so here by the round number 4, phi j has no residue, and so we may conclude that Cj must be 0. Now, after rotating a surface, we may assume that the Gauss image at P1 is equal to I, 1, 0, 0 in P3. So in the end, we have the following expression. In part 2, we use this expression, and with the special choice of its differentials, we will prove the main results. So this is the end of part 1. Thank you for listening, and see you in part 2.